talk a little bit about data collection, how to extract, and how to transform the data that you find in your literature review. Okay, so there's a lot of different ways you can collect data. You can measure and collect experimental data on your own in the laboratory. You can take data that you've previously produced. You can reuse another researcher's data, which is what we're asking you to do in a literature review. Or, worst case, is you purchase data such as what you can from a database. There are a lot of databases on campus through the library system that you can use, and those are examples of purchased databases. So I'm going to talk about others' research, how to examine it, how to analyze it, how to transform it. So once you've established a data set and you've verified its credibility, and when I say credibility, you want to see that there are more than just one literature review on the subject, that you reorganized it, you may have applied some transformations to it, and then you can extract it for visualization, meaning you put it into bar charts or linear charts for regression analysis. Now, the other thing you also want to look at is, can you detect patterns in the data so that you can better understand how they describe the observations or support the observations that are part of your hypothesis. Okay, and an analysis of variance is one way to do that. That way, then, once you've transformed it, the results you get from, say, a literature review, you can visualize and interpret them in the context of your own hypothesis. So just an example, here's a chart on the left and my plot on the right. I eliminated going to the intercept of a zero origin simply because in the research paper they hadn't explained or demonstrated that they'd actually taken a zero sample. So you can't assume that it's necessarily going to go to zero. Some things intercept later, or the linearity changes. And you can see in the original graph it's more of a power function. So what I did was I eliminated that, and then I created a bunch of polynomials to explain the different levels, in this case peracetic acid versus hemicellulose in time. So this is an example of how to transform the data. In this case the data still looks pretty much the same, but the regression curves I got were slightly different. Just a couple watch-outs though. When you extrapolate data, you may not always have the entire data set. There's some assumptions we make. So in the case on the left here, you can see that you have a regression line, and here's the number perhaps that we want, way up here. That's our predicted value. But in reality, if they had continued to take the experiments the true regression line is here, and that's very similar to, say, brightness development on a bleach plant, right? You tend to reach an asymptotic limit. Here's just a graph for fun. The frequency of the use of the word sustainable in the English language per year, and with extrapolated out by the year 2109, we won't be seeing anything but sustainable. Okay, so kind of an extreme example of how a predicted value, there's a little bit of a watch out. Here's another example where all of these data sets have the same R-squared correlation. All of them have been given a linear regression with the same slope. But you can clearly see that this is a data set 2 here, a nonlinear line. You can see here that this linearity here, and this is probably an outlier. And of course, this data set with this data point is clearly, this probably is an outlier as well, or potentially so. But here are examples where you've applied a linear regression to 4 different data sets and got the same exact results. Okay, so it's important that you understand the data set, what the researcher did, and that's why I say it's good to see if you can find at least 2 research papers, because a lot of times a researcher will have a problem and it overlaps or dovetails with somebody else's research, or it's an extension of somebody's research. And so you might have to, in order to create the entire data set, use data from several different papers. All right. So where I always start, and this is my strategy, is I always try to frame my problem statement as simply as possible, but it gives me a starting place for my literature search. So for me, for this example, I wanted to see how hemicellulose responded to peracetic acid in an acid hydrolysis step, basically sulfuric acid. When I first started looking up this in the literature, I found absolutely nothing. So I went back and said, okay, let's try to cast the net a little wider and use fewer keywords. And this is the paper I found. It's titled "The Effect of Several Factors on Peracetic Acid Pretreatment of Sugarcane Bagasse for Enzymatic Hydrolysis." It's not for pulping, it's not for bleaching, right? It's okay if the research article doesn't specifically state or is in agreement with your problem. In this case, I was lucky. The paper included all the conditions that I needed. It measured the initial responses of the treatments with regard to cellulose and hemicellulose. I just needed to massage the data a bit so that I could answer my question, but it was there. Okay. So the first thing I did, I decided to start transforming the data just a little bit. Here is their graph on the left, and you can see a couple things. They were looking at cellulose here, first conversion. This is the same as liquor to wood ratio. They just called it liquor to solids ratio. Their charge of peracetic acid and the trends. So I decided, you know, with a little bit of the knowledge I had about acid hydrolysis, I wanted to start my first transformation and plot it versus the concentration of sulfuric acid and xylose yield, looking at what was the impact of the peracetic acid on that process. So I separated that out. And as you can see, the trends are not that much different, but there's a lot of variation. This trend here goes in power. These are all somewhat exponential, so not a lot of agreement in the data. Okay. So that, because I wasn't satisfied with my replot of the data, and then here's a little exploded view of it, so it's a little easier to see, I decided to continue to transform it. So one of the things I noticed was the author expressed his results as a percent applied on OD wood. However, he was changing the liquor to wood ratio, so in a sense the concentration. But he didn't account for that in his trends. Okay, so I replotted accounting for the change in concentration. I kept them saying, you know, sulfuric acid on the bottom, and so now here's the trends against molarity of sulfuric acid. The one thing I noticed here is that the molarity difference is quite small. There's not a lot of difference in molarity. So perhaps what I should have been looking at is, instead of the molarity of sulfuric acid, the molarity of peracetic acid. So what I've done so far is I've taken into account the effect of liquor to wood ratio, so that the data, as I visualize it, is a little different. Change the curves slightly. These curves are a little more linear. The 60% is still kind of out there. But it appears, for example, like I said before, that the sulfuric acid does shift the curve at small concentrations, does shift the curve up. Okay. So calculating the molarity of the peracetic acid, I'm going to replot that data and see what trend I get. So as you can see, it became very linear once I did that. Now this trend is independent of liquor to wood ratio, right? So I've taken that into account in the molarity calculation. And now the plot is based on an intensive property rather than an extensive property. So the extensive property being liquor to wood ratio. So now I have my R is not super great, 0.87, but now I've got a relationship between the application of peracetic acid on xylose yield. So then what I did was I said, okay, now let's take a look and see what the effects are. So I did an analysis of variance to see what was contributing to the yield of xylose and the yield of glucose. So the first thing we see is that the concentration of sulfuric acid and peracetic acid both have an effect on xylose. In this case, when I did the analysis, this number here is 77% of the total variance in the data set is attributed to the sulfuric acid content. And only 9% is contributed to peracetic acid. A little bit surprising considering what I know about peracetic acid and what I thought was the significant interaction. Here, this is the interaction. It's not significant. And again, the literature would suggest that peracetic acid aids or has a compounding effect with sulfuric, and we're not seeing that there. Same kind of trend with glucose. Sulfuric acid is 87% of the total variance, and peracetic acid is insignificant as given by the p-values over here. Okay. So let's take a look at arabinose. If you recall from the lecture on hemicellulose, peracetic acid goes after the ferulic acids, and those are primarily attached to the arabinose. So this researcher had data on arabinose. So I did the analysis of variance there, and now you see that peracetic acid, the contribution or the explanation of the variance in the data is 20%. Still, no interaction here, but this is promising. Sulfuric acid, still 42%. So that's consistent with our hypothesis that the peracetic acid reacts with ferulic acid groups attached to the arabinose and xylene. So remember from this drawing here, there's their ferulic acid, and here's your arabinose units on the backbone of the xylose. So the other thing we can do, and this is more just an aside, this is more of a deep dive, we can do a principal component analysis and look at the eigenvectors of each response. And what that does is it isolates the variables. It looks for the maximum variance in the data set relative to the treatments. And so when I plotted that, these vectors correspond to the magnitude of the contribution. Now you can see something different. If you looked at the original graphs, you would assume that glucose has a significant portion of the data set. In reality, arabinose here is explained by one of the principal components, and xylose yield the other. So this is much more consistent with what we would expect of the data, but without doing this analysis, you don't get this information just from your analysis of variance. So I decided to take a look at the original hypothesis of this paper, and the author made these 4 claims: that cellulose content increases with increasing PAA, lowering the concentration of peracetic acid reduced the yield of cellulose, sulfuric acid played the major role in glucose yield, and increasing the molarity of the peracetic acid resulted in a decrease in cellulose concentration. What I found with all these analyses, that there was no significant correlation between cellulose yield and peracetic acid concentration. I did agree with these 2, that the molarity of the peracetic acid was indeed correlated to arabinose yield, but only to a small degree with xylose yield. So likely the peracetic acid increase in that molarity activated hemicellulose to sulfuric acid attack. Sulfuric acid played the major role. Yep, we agree. It accounted for 87% of the variance in the data set. However, a plot of molarity versus the xylose yield indicated that peracetic acid had no impact negatively in decreasing. It actually increased. So this wasn't always the result we expect. I mean, the author had data that I needed for my problem, even though the problem was not within the scope of my question, right? His research was expressly looking for the impact for producing ethanol. And unfortunately, I refuted some of his conclusions simply by taking his data and massaging, transforming it, and doing some additional data analysis on it. This is, of course, an extreme version, not what we'd expect you to do, but I wanted to demonstrate what you can do with data. And just final words. There's a lot of data out there. Correlation can be found where none exist. So you need to be really careful in how you apply linear regression tools and how you data mine. Because you may find that there's correlation in things that seemingly have no correlation. For example, people who drowned after falling out of fishing boats and the rate of marriage in Kentucky.